closure. And I think later, sometime, he will give another talk which is independent of this about Reising numbers. So today's talk is about absolute integral closure. And this is the first of 3 talks that we have arranged on absolute integral closure. The next 2 talks will be by Manoj Kumini, where he will continue with whatever is covered today. So Arindam, you may please start now.
Okay, so I just want to start with thanking Professor Verma and Jayantan and all the participants. I mean, this was a really interesting event, and this made our rather stressful lockdown days a little more bearable. And we just experienced many fantastic talks. I also want to apologize for slightly tweaking the title of my talk, because it was supposed to be Introduction to Absolute Integral Closure, but I couldn't help but put Newton-Puiseux Theorem there, because that theorem will be also sort of an important topic of this talk. By the way, can everyone hear me clearly? I'm hearing an echo.
Yes. Yeah, it is very clear to me.
Okay. Okay, let me start with some very basics, and I'll try to go as slow as possible. I mean, because I'm supposed to do the basics from which Manoj will pick up. So I'm assuming all rings are commutative with unity. Let's begin with a definition. I mean, this is standard definition of integral closure and so on. So let R be a domain and S be an extension of R. The integral closure of R in S is the set of all elements small s in S, which satisfies a monic equation with coefficients in R, where basically S power n plus summation Ri S power whatever, that's equal to 0. If this equation is satisfied, then called S is integral. Elements in S which are integral over R form a ring called the integral closure of R in S. One needs to prove this thing is a ring, but it's fairly elementary. It's fairly straightforward to prove that all elements that are integral, that forms a ring. If S is the field of fraction of R, then the resulting ring is called integral closure of R. And R is called integrally closed if it's same as R. It's fairly elementary to prove that every UFD is integrally closed, and also we know that if R is integrally closed, then so are polynomial rings and power series rings, so are R, infinitely many variables.
Arindam, may I interrupt for a second?
Yeah, sure.
Can you adjust your screen, because we don't see your face? It is being recorded. We see only your head. You may be using iPad, so you can realign it. Yeah.
Can you see?
Yeah.
Okay.
But maybe a little bit more.
Okay. Can you see me now?
Yeah. Yes. Please. Yeah. Now you can.
Okay. Yeah. Actually, I'm okay. That's never mind. Yeah, that's okay.
Yeah.
So let me first define this big thing, which is the main topic of today's talk: absolute integral closure. Let R be a domain with a fraction field, and take any fixed algebraic closure of the fraction field. Then the integral closure of R in that fraction field, denoted R plus, is called the absolute integral closure of R. And now this thing, by the way, this is a fairly big ring, and this is almost always not Noetherian. To study R plus, let's first point out that it's enough to assume that R is integrally closed itself. By the way, let me a priori announce that I'm following Professor Uniki's notes on this topic, and at the end of the talk, I'll just mention which notes I'm following. So we'll first show that it's enough to assume that R is integrally closed itself. Now, let's S be the integral closure of R, and then obviously S is inside R plus, because S, after all, elements that are integral over R inside the field of fraction, and which sits inside R plus. So that automatically shows that S plus is equal to R plus. So more generally, if S is any finite integral extension of R, which is a domain, then fraction field S is algebraic over fraction field of R, and hence there exists an isomorphic copy of S that contains R and sits inside R plus. So any questions so far? Because just I'm just fixing the definitions and so on. You know, lots of PhD students are attending. Any question? All the definitions are clear, definitions and conventions. Okay.
Excuse me.
Okay. Okay, let me. Yeah. So what is it?
Excuse me. Excuse me. Do you assume that the rings are Newtonian?
Sorry, do I assume what?
Do you assume that the rings are Newtonian?
To begin with, sure. I mean, it doesn't hurt to assume. Let's. But R plus is not Noetherian. We can assume. I guess we can. I don't remember when exactly I need it, but it doesn't hurt to assume, I guess, for most of my talk. But R plus will not be Noetherian.
Thank you.
Anything else? Okay. So we'll just assume from now on that S sits inside R plus, hence S plus is equal to R plus. And studying R plus, by the way, so it's basically studying all integral extensions of R at the same time. It's all of them sits inside R plus. Note that when R is local and complete in M-adic topology and contains a field, then R is actually a finite integral extension of a formal power series ring of over a field K. Why? I mean, why this is true? Well, because of Cohen structure theorem. The Cohen structure theorem gives that there exists a field K inside R such that the composition of maps K inside R mod M is an isomorphism. Also, if x1, x2, xd is a system of parameter for R, then complete local subring of R generated by these elements, K, x1, x2, xd, the power series ring, is isomorphic to formal power series ring, and R is module finite over A. Hence, A plus is same as R plus. This is a very subtle point which makes, it essentially says that it's enough to study formal power series rings only. So if you want to study these R pluses, then it's enough to study these rings only. And so that will make our next main theorem that we are going to discuss. We'll actually discuss two main results. The first one is a complete description of R plus when R is power series ring over a field in one variable. And this essentially, this observation which comes as an immediate corollary of Cohen structure theorem, makes the study of power series rings in this context so central. Yeah, what's the question? I think there is a question, right?
Are you assuming R is Noetherian now?
Yeah. Yeah. Let's assume R is Noetherian. Okay. Let's assume R is Noetherian. Let's assume R is Noetherian henceforth. So, if a copy, this is what we are sort of discussing. If a copy of the residue field sits inside R and it's fixed, then R plus is unique for each dimension. It is the absolute integral closure of the formal power series ring.
Arindam?
Huh?
So there's this question, is it actually needed? That is the question. That's what, do we need to really assume that R is Noetherian?
Well, so far, I mean, I'm just trying to recall whether Noetherian is needed for the Cohen structure theorem, but I guess no.
Yeah, that's the question for this. Another question from Nina asked.
So I think
Okay,
for Cohen
Kamran clarifies that.
Yeah, for Cohen structure theorem we need more theory. Yeah. Okay.
Yeah.
Yeah.
And Nina is asking, what do you mean by each dimension?
Well, because essentially for each dimension we have one power series ring, formal power series ring. So it is enough to study the
Okay.
absolute integral closure of that. Any further question? Okay. In other words, we're just really basically studying one ring, the absolute integral closure of power series ring. There is a classical theorem which we'll talk about, which gives the structure of such a ring in dimension 1 over a field of characteristic 0. An important observation: if R is an integral domain, then a domain is integral over R is isomorphic to R plus if and only if every monic polynomial over S factors into monic polynomials over R's S. So I'll just, for now, I'll mention a few properties of absolute integral closure. I don't think I'll be able to prove all of them, but I'll prove at least one of them, which basically is a theorem by Michael Artin. So the first one is this one, that a domain S is integral over, which is integral over R, is isomorphic to R plus if and only if monic polynomials over S factors into monic linear polynomials over S. Some properties of R plus. The first one is basically it commutes with localization, where the second localization is essentially with respect to the multiplicatively closed set R minus Q. The same is of course true for the first one also, but that's just the usual localization at a prime ideal. So absolute integral closure of localization is the localization of the absolute integral closure. This actually isn't very hard to prove. I mean, just writing the equations will give it. The next one probably needs a little more work. It just says that you take any prime ideal in the spectrum of this absolute integral closure. If you go mod that prime ideal, then that's isomorphic to essentially go mod the ring. So the quotient the ring with restriction of the contraction of that prime ideal, and then take the absolute integral closure. So basically, every quotient of R plus is itself is an absolute integral closure of some appropriate quotient of R. The next property is an interesting theorem by Michael Artin. So it says that if R is a domain and P and Q are prime ideals in R plus, then either P plus Q is R plus or
Arindam?
Yeah.
I have a, can you please go back to the previous slide?
Yeah.
Just so if you take any, I mean, just any P prime ideal of R, and then look at R mod P plus.
R mod P plus, okay.
Yeah, so I mean, that will also I mean, see here, you want to say that both ways it's true, right? Any take.
Yeah. Right.
You take an R mod, I mean, spec Q in spec R plus. That will appear as a as an extension of a.
It's just lying over, right?
Sorry?
It's just lying over, yeah.
Lying over.
I mean, for any prime ideal, it's an integral extension.
Yeah, okay. R plus is an integral, yeah. And it's an integral extension, yeah.
Yeah, any further question?
No.
This one? Okay. So the next one is this theorem I was talking about by Michael Artin, that if R is a domain, and if P and Q are prime ideals in R plus, then the sum of P and Q is either R plus or their the sum is a prime. Now, note that this is a very sort of unique kind of property, because this doesn't really hold for most of the familiar rings. I mean, for example, take kxy, the ideals p, even these principal ideals p, where p is x plus I x, y square, and q is x, they are prime, but their sum is not prime, and of course their sum is not the whole ring. So this is a very unique kind of property, and the proof is rather elementary. So to prove this result, let's take AB in P plus Q, set Z equal to B minus A, and notice that this thing holds, because first of all, AB is in P plus Q, so it's sum of U plus V, and that essentially means that if you compare with this equation of Z, you get this equation. The equation x squared plus zx plus u has a solution x in R plus, of course, because this is the integral closure inside the algebraic closure. Since u is in P, it follows that either x plus z is in P or x is in P. That's because P is prime. But not x squared plus zx minus a squared plus za equal to u minus u plus v. So either x minus a is in Q or x plus a plus z in Q. And that sort of this thing comes from factorization of this. So, this thing, it's just elementary, like high school algebra, like x square minus a square, and you have z times x minus a. So you just combine these things and you get this equation. So in each of the 4 different possible cases that you get, we obtain either A is in P plus Q or B is in P plus Q, giving us the result we are looking for. For example, if x plus z is in P and x minus a is in Q, then B equal to x plus z minus x minus a, this is inside Q. And you can sort of do the other cases in this way. I'll come to that later. So this is the proof of this result. Is it okay? Is the proof of this result okay? Any question on this particular result? No question? Okay. Let's go to the next one. Suppose when R is complete local, every finite extension domain of R is also local. So if R plus is a local, so R plus is a local ring. So P plus Q equal to R cannot happen. And the sum of every set of prime ideal is prime. So this together makes this ring R plus something of very unique property. Let K be a field of characteristic 0 and consider the formal power series ring K in one variable, whose field of fraction is denoted by K double round bracket T. By the way, this is the field of LoRa series. So this KT, the power series, is essentially an
Arindam?
Yeah.
There is a request from Raghavan. Can you please go back to the previous slide? Raghavan, if you have a question, you can unmute yourself and ask. I think that's fine.
No, I just wanted to see the last result. It was too fast.
Oh, sorry. I'll try to go slow. Yeah.
Thank you.
Okay. Can I move on?
Yes, Arindam, thank you. Yes.
Yeah.
Yes, Arindam, thank you.
Yeah. So this field of fraction of this power series ring is essentially the LoRa series ring, which essentially means, power series ring means you can have terms for all positive powers and no negative power at all. All positive powers and a constant term. And the Laura series is essentially just what we know about Laura series from complex analysis. Like all possible positive powers can stay and only finitely many negative powers can stay. So that's the field of fraction of power series ring. A famous theorem due to Puiseux, hope I'm pronouncing the name correctly. Puiseux is the correct pronunciation, right? Okay. So this is apparently, it's a famous theorem by Puiseux, but apparently known to Newton, that algebraic closure of the Laura series ring, this K double round bracket T, is actually union of these fields, K double round bracket T to the power 1 over n, where 1 is a positive integer. And this is true in case of characteristic 0. Kiran Kedlaya gives a characterization of algebraic closure in case of K has positive characteristic. We'll come to that characterization slightly later. But it's very different from characteristic 0. So it's very much dependent on characteristic. Actually, Chevalier pointed out that the so-called Artin-Schreier polynomial x to the power p minus x minus t inverse has no root in Newton-Puiseux field, this union of these things in characteristic p. So basically, in characteristic p, this is not basically algebraic closure of this Laura series field. And so there are remarkable differences in R plus, the structure of R plus, depending on characteristic of the ground field. Any question in this slide? On this slide, I mean. By the way, please let me know if I'm going too fast or too slow, because I'm not being able to see the faces. So it's really difficult for me to guess whether I'm becoming too fast or too slow. Please stop me if I'm going in the inappropriate speed. So this is the Newton-Puiseux theorem. If K is an algebraically closed field of characteristic 0, suppose take this Laura series field, which is a field of fraction of the formal power series ring, then algebraic closure is the Newton-Puiseux field we discussed. Here n can vary over all positive integers. The proof of this result, so we'll come to the proof, but as a corollary, we get the following. The absolute integral closure of this power series ring is union of these, these rings, namely the power series union runs over all positive integer, and then you take power series in t to the power 1 over n. That's the absolute integral closure. And this, by the way, is the connection between these two topics in my title, like the Newton-Puiseux theorem and the absolute integral closure. The proof of this corollary is essentially an immediate, this follows immediately almost from the Newton-Puiseux theorem. And one key ingredient for this proof is a version of Hensel's lemma, which essentially says that you take a Noetherian local ring which is complete in M-adic topology. Then you take a monic polynomial with coefficients in R, such that when you go modulo the maximal ideal, it factors into product of two relatively prime monic polynomials of positive degree in that field, over that field. Then this factorization lifts into a factorization of Ft into two monic polynomials over R. So basically, if you can factor a monic polynomial in the field, then you can lift that factorization into a factorization over the ring. That's the version of Hensel's lemma we'll use. Are the statements clear? Statements of all three? I'll go to the next slide. So the proof of this, I'll just do it sort of in one stroke. The proof of this theorem and the corollary. We need to show that every monic polynomial Pz over this ring is irreducible. That will be enough by this thing called Gauss lemma, that you can factor something over a domain even only if you can factor it over the field of fraction. So it's enough to show that this is irreducible. Now we use this transformation for the proof. Well, not me. I mean, in the theorem they use this transformation, And by the way, as I said, I mean, I'm following these notes by Professor Hunicke, and all these proofs are from his notes only. So we use this Scharnhausen, I think the pronunciation, transformation, just to make basically the coefficient of the n-1th power 0. That is, you have a polynomial z, monic polynomial z power n plus a1 z power n-1 dot 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 an. You basically take the transformation z prime equal to z plus 1 over n a1, and this basically will make the, if you do use this transformation, you will see that n-1th coefficient doesn't appear. So that is what that it will need. Now replacing, we can replace, of course, this ring by k t to the power 1 over n for some large n, and we can change variable to assume that all the ai's are in this power series ring. Now we use this odd as this t-adic order of an element, and we write every ak as basically a unit times t to the power rk. And finally, want to factor pz. And to do so, we'll use Hensel's lemma. Sorry, there is a typo. I meant 1-2 factor. So is this clear? The setup is clear. The transformation we are using and this notions and of order and why we are doing this. You know, we are assuming this AIs are in KT and so on. Okay. So enough to factor PZ into two relatively prime polynomials after going modulo T by Hensel's lemma. This is possible unless after reduction mod T, PZ becomes basically product of T minus alpha power n for some alpha in K. Basically, it's just power of a linear term. Unless this happens, it is possible. Now, as AI is 0, I mean, note that if you have this T minus alpha power n, there is no way you can get AI to be 0. So the only possible, and we are in characteristic 0. So the only possible such case is alpha equal to 0. And so we are done unless for every k, the AI zeros are 0. And basically what we do, we just make a change of variable where this thing doesn't occur. Oh, sorry. Any question for these first two slides? Okay. So now take this transformation z equal to the power ry, and we'll just basically choose this r later so that what we wanted will happen for that r. But for any such r, if you have this transformation, then pz becomes this. And remember that we already first made sure through a transformation that a1 is 0. Want to factor out t to the power rn from every term in such a way that at least one term becomes a unit. The power of t dividing the ith term is this, t to the power I times t to the power n minus I r. So need to choose r in such a way such that ri plus n minus I r greater than equal to rn. That is so that ri greater than equal to r. So basically set r equal to minimum of r mod I. With this, we can rewrite pz to be t to the power rn q yt, where q is y to the power n plus b2 y to the power n minus 1 dot 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 bn, and replacing t by t to the power 1 over n for suitably large n, we can assume that each bj belongs to kt. So is it okay so far, all the transformations and calculations? You're basically doing fair amount of change of variable and making sure that certain coefficients behave in certain way. So there exists BI such that this BI non-zero, BI0 is non-zero, and this happens for every term where Ri mod I is R. This follows that we can factor Q over the residue field into relatively prime polynomials, and by Hensel's lemma, this lifts into a factorization of Q, and Q is just, recall that Pz times this. So factorization of Q will give us a factorization of P. The ring in the right hand side of so this basically finishes the proof of Newton-Puiseux theorem. After this, we prove the corollary where we essentially prove that result for the integral absolute integral closure for polynomial ring in one variable. The ring in the right hand side is clearly an integral over kt, and the fraction field of its is clearly the Newton-Puiseux field. I think these two are fairly clear, which is an algebraic closure of that. To finish the proof of the corollary, we need to prove integrally closed, but this is basically union of discrete valuation rings, each of them integrally closed, so it is also integrally closed. So that basically proves the Newton-Puiseux theorem and the statement about absolute integral closure of power series ring in one variable. Let me stop, pause here, and take if you have any question. Any question?
I have a question, Arindam.
Yeah.
So in the first slide, you stated some properties of absolute integral closure about going mod Q and localization. And what about suppose you construct absolute integral closure of a local domain R and then take polynomial ring over it? Then can we relate the two absolute integral closures?
Sorry?
I mean, what's the relation between Rx plus and R plus X? Or X is there? Can we have a Newton-Puiseux type theorem in characteristic 0 for this?
Sorry, Professor Verma, can you repeat the question once?
So how does absolute integral closure construction behave with respect to adjoining a variable power series wise or polynomial ring wise?
Oh, so instead of power series, what happens if you do polynomial ring?
Yes.
Is that? Yeah. Okay. I actually don't know. Yeah, I don't know.
Yeah. So, I mean, similar theorem is not true.
Similar theorem is not true?
I mean, I'm asking if you change it to polynomial ring in one variable.
I don't know.
Because you use Hensel's lemma, which used that it is complete. And
yeah.
So one can't give that argument.
No. One cannot give that argument.
Yeah, but so for absolute integral closure of polynomial ring in one variable, we don't have this. At least the proof will not work.
But did you also ask something like whether absolute integral closure of polynomial ring is polynomial ring over absolute integral closure? Is that what you asked?
Yeah, that will not be true.
Yeah.
If you take just a field,
right,
which is algebraically closed, absolute integral closure is itself.
Yeah. Okay. Okay. Yeah.
Hi, Arindam.
Huh?
Hi, Arindam. So I actually have a question. Hello, Arindam.
So yeah.
Actually, yes. So what you proved so far tells us that the power series ring in T to the power 1 upon n is integral over the power series ring in T.
Is this on?
At least this much.
Is this Onjan?
Yes,
by the way?
I am Onjan. Yes,
okay. Okay. Yeah. Yeah. Go ahead.
Yes, I am Onjan. So what you proved so far, it follows that power series ring in T to the power 1 upon n is integral over power series ring in T.
No, so you have to union of T to the power 1 over n. Yeah. So yeah.
At least integral, I'm saying that. So I just want to see the equation. Yes. I just want to see the equation of integral dependence of the power series 1 upon 1 minus T to the power 1. See, let me see, 1 upon 1 minus t to the power 1 upon n is 1 plus t to the power 1 upon n plus t to the power 1 up to 2 by n and so on, right? Can you show me can you tell me the equation of integral dependence of this element over the power series in T? Just a simple example.
Which one?
So if we consider the element, if we consider the power series in t to the power 1 upon n,
t to the power 1 upon n, okay.
which is 1 plus t to the power 1 upon n plus t to the power 2 upon n plus t to the power 3 upon n. It is basically 1 upon 1 minus t to the power 1 upon n. So can you show me the equation of integral dependence of this element over the power series in T? I just want to see an example. I'm not able to figure out the equation.
Sorry, Anjan, I'm extremely sorry. I didn't really follow your the series.
Okay, we discuss it later.
Okay.
We'll discuss it later.
Yeah, I am hearing an echo and I couldn't hear. Okay, yeah, we can discuss later. Yeah. Okay, I mean maybe after the talk. Yeah. Okay. Anything else? Any other question? So I'm just slowly going through the proof once more, the slides of the proof, in case somebody. Okay, note that this actually gives a complete description for power series ring over in one variable in characteristic 0. However, in characteristic P, the picture is really different. As an example, consider this equation which we actually talked about earlier. X squared minus x equal to t to the power minus 1. Using the quadratic formula and Taylor series, one can show that roots of this polynomial are actually power series in t to the power minus half. And one can sort of recursively solve the coefficients. And this is drastically different in case of positive characteristic. A generalized power series, we will need this notion to describe it in case of characteristic P, is a power series expression of the form summation I ci e to the power I, ci is equal to k, and such that basically, you know, set ci for which, sorry, I mean ci is not 0. I did ci is not 0 is a well-ordered subset of Q. That is a non-empty. Every non-empty subset has a least element. Such notion of generalized power series comes from all these such power series forms a ring in natural way, just like usual power series. Makes sense to multiply and add them in obvious way. Abhyankar pointed out that with this generalization of the idea of power series is Chevalier polynomial. This has a root t to the power minus 1 over t to the power 1 minus 1 over t square and so on. So are there enough generalized power series to obtain an algebraic closure of k to the power k double bracket t in characteristic P? So this theorem by Huang, Rayner, and Stefanescu is important to describe that. Suppose K is an algebraically closed field of positive characteristic, and let capital K be the set of generalized power series, where this support S satisfies the following properties. S is a subset of Q that depends on F. Every non-empty subset of S has a minimal element. And there exists a natural number m such that for every element ms has denominator of a power of the power of p. Then K is an algebraically closed field containing a double bracket t. Further, this series summation ci to the power minus 1 to the power I, with ci is belonging to this algebraic closure of field with p elements. This is algebraic over this if and only if the sequence is eventually periodic. Using this result, this is a sort of a powerful description of some interesting properties what happens there. Kiran Kedlaya gives this result, from using which he actually gives a description for absolute integral closure in characteristic P, which kind of is that absolute integral closure is difficult to describe, but these theorems gives an idea how how different the things in characteristic P.
What is capital K in the first theorem?
Hello?
What is capital K? Then K is algebraically closed field containing K Lorentz series.
No, capital K is the generalized power series. The K is the...
Oh, okay.
Yeah.
Okay.
Yeah, the statement is K is an algebraically closed field containing this. K is first, so we are defining K to be this set, and then they're asserting that this is an algebraically closed field containing K. So what Kerala says is that if small k is an algebraically closed field of characteristic P, and suppose F is a generalized power series, which is algebraic over K double bracket T double round, then for every real number alpha, if you truncate this series up to alpha, then this is also algebraic over K. I mean, this is a crucial theorem using which he gives the description of both algebraic closure and absolute integral closure. Okay, next I'll move to a slightly different topic, but let's see if there are any further question here. So, okay, so this gives a sort of finishes our discussion on absolute integral closure of power series ring and its explicit description. So next, let me recall a few very basic definitions. That a sequence of elements x1, x2, xd in a ring is said to be a regular sequence, the usual definition. If Rxi inside this 0 to xi minus 1 implies R is there. That is when you go modulo that xi is a non-zero divisor. And when you basically take the ideal generated by this whole set, that doesn't generate the whole ring. And let Rm be a Noetherian local ring of dimension D. Elements x1, x2, xd are said to be a system of parameter if nil radical of the ideal they generate is basically the maximal ideal. A Noetherian local ring is Cohen-Macaulay if some, and actually one can prove that is equivalent to say every system of parameter forms a regular sequence. Just to recall some of the really basic definitions. So this is an important proposition that we'll mention. And by the way, this is going to be the last really big theorem I'm discussing today. And I think Manoj will pick up after this. That if A is a power series ring in D variable, where K is a field of characteristic P, and the following two conditions are equivalent. x1, x2, xd forms a regular sequence in the absolute integral closure, and absolute integral closure is flat over the original ring. So let's first assume one, that it's this. Suppose that then suppose this is true, that it forms a regular sequence, and suppose a plus is not flat over A. Now let's choose I as large as possible so that tor IA bracket A mod P comma A plus is non-zero for some prime P in A. Such a choice is possible because A is regular and large tors vanish. If y1 data ys is a maximal regular sequence in P, then one can embed AP in A mod y1 ys, and as P is a minimal prime, A mod P can be embedded. Minimal primes are associated, and let C be Cohen. As C has a prime filtration, we have this tor. This is 0. Well, this holds essentially because for every short exact sequence, m prime m double prime 0, we have this long exact sequence of tors. Now, since C has a prime filtration, you can basically construct C through a sequence of short exact sequences where each successive quotient is essentially the ring mod a prime ideal, and the ring mod the tor I plus 1 for ring mod prime ideal and A plus is 0 because of the way we have chosen I. Hence, inductively we'll get tor I plus 1 C A plus is 0. So with this, we have this particular tor is 0. As for any prime filtration, so this is basically what I was saying, that successive quotients, these tors are 0, we get the required. Next, we note that if y1, y2, ys, the one we have already chosen, form a regular sequence on A plus, then we have, if this is a regular, well, using regularity, we will have, this is 0, because it will be, you take this essentially, you take, sorry. You essentially come to this construction that A mod P sits inside this, and then you have this co-kernel C, and if this is regular, then tor with that quotient will be 0, and tor with this is 0, and hence this is sandwich between two things, and using long exact sequence, we'll have this tor 0, but then this tor is simultaneously 0 and non-zero, so which gives us a contradiction. And note that this uses the fact that this is regular. These are regular on A plus, but otherwise this is not true. So to finish the proof, we need to prove that this forms a regular sequence. To see that this is regular sequence, well, basically you extend it to form a system of parameter, and suppose B is this ring, and then B plus equal to A plus, and by hypothesis we'll get Y's form a regular sequence. And to prove the other assertion, it's enough to observe that flat maps is a regular sequence in general. So that sort of completes the proof. Let me take a moment and address if you have any question regarding this. Anybody has any question regarding this proof? Should I sort of browse through once more? Any question? Any question or comment? Let me quickly go through the proof. So this is what we are trying to prove, that basically this forming a regular sequence and flat over A, they are equivalent.
Arindam, in the statement,
Uh-huh.
what are the? I mean, I'm a little confused with the following are equivalent. It says these are conditions for the field on the field K. It's a power series ring, right? To begin with.
Uh-huh. No,
So
but yeah.
I mean, either it is true or not. I mean, so I'm a little confused with the proposition. These are conditions on the field K. I mean, depending on field K, these conditions could be true or false.
So at least the statement of this proposition says so. Yeah.
Yeah, but the what could differ is depending on the field.
Yeah.
Oh, I see. It varies on P as well.
Yeah.
I see. Thanks.
Okay, so this is the last big theorem I'm going to prove, and so basically, what I heard from Dr. Verma that Manoj will sort of go into this Cohen-Macaulayness and the other things, but where do we go from here? So what we essentially prove that absolute integral closures of an excellent local domain in positive characteristic is Cohen-Macaulay in a suitable sense. Well, so absolute integral closures are not Noetherian. So what does really Cohen-Macaulay here means? Well, Cohen-Macaulay essentially means that any system of parameter coming from A will be regular sequence in A plus. And so I just want to mention one application I saw in Professor Uniki's notes, that there's a theorem by Brodmann and Rung. Basically, this says that if Rm is a complete local Noetherian domain of dimension D, and suppose x1, x2, xd is in M, then the punctured spectrum is connected. And so basically, using absolute integral closure, Professor Uniki and Professor Hofstad gives some proof in case of characteristic P, so which is kind of interesting to see the proof. So I just, okay, so this is what I planned. So I'll stop here. So let me see if there are some questions. So I'll stop here. Yeah.
So this theorem of Broadbent and Runge